Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
Good evening, all. I hope you all doing well.
Yeah, hi. Good evening, Sushmita. And good evening
Yeah,
to
good
all
evening.
of you.
Yeah, you can start the session.
Yeah. Sure. Thank you. A very good evening to everyone. Uh, so yesterday actually we left some of the concepts, and also I have to show you some practical designs. Practical designs means this type of designs actually we are applying, means if we are seeing that whatever the design notes actually we are having, and also there are multiple companies are there, especially we means we left the charger part. So how actually we can design a onboard charger, right? So that is our main motive, to design an onboard charger. Obviously there is a multiple companies are there who have their own design notes, their own integrated chips. So dependent on their working actually, they already have their reference designs or reference boards. So today we will see some of means one of them example. So let me share the screen first. So yesterday we left with two technology. One is the V2G G2V technology. So 1 second, guys. So we already cover these things, that PFC circuit requirement, right? As per uh, yes, as per the design rules and the standards, actually nowadays you have to use PFC circuits basically to improve the power factor. So in case of charger circuit, we use AC to DC conversion. So mostly whenever actually we need a AC to DC conversion, on that case actually we have to use a power factor improvement circuit. So that is PFC circuit. Also in PFC concept, there are multiple types of actually means topologies actually we are using. So I am not going into deeper on this type of technologies, but yes, obviously we there are multiple research actually are going on this PFC circuits, especially for higher kilowatt I am talking about, because obviously whenever we are designing an onboard charger, so roughly they are means they are starting from nearly 3 kilowatt, 4 kilowatt, 5 kilowatt, 7, 10 kilowatt also are available in the market. Okay. So our actually this is a data sheet, means how actually we are implementing these things and why also we need PFC circuits. You can see that the first one, the first parameter on the supposed to be, this is a charger specification sheet, right? In the charger specification sheet, you can see that the AC input range, that is from 110 to 285, right? Obviously we don't know in India in any cases, means 230 is not stable, right? If I am talking about the transmission lines, 230 is not stable everywhere. So somehow we are getting 250, 260 volt as well. Somewhere actually we are getting 180, 170 volt as well. Nearly 150 volt also we have seen. So that is why nowadays, whatever the charger actually we are designing, not only for EVs, for cell phone charging and any type of other charging systems, actually we are using PFC boost circuit. So suppose your input voltage also varies from this range, right? Mostly this type of means range actually we are using. We can say this is a standard from 100 to 300 volt. So in between this range actually we are operating, and nominal obviously that is 230 RMS. And you can see that AC line frequency also, if the line frequency also changing from 47 to 63 hertz, it can operate easily, means it can charge your vehicle easily. And you can see that the power factor, So they are giving the power factor greater than 0.98 at full load. And also you have to put the efficiency. So depending on the input voltage, actually the efficiency is changing. You can see that from 180 volt to 285 volt at full load, we are getting the efficiency greater than 92%. And from 120 to 180, that is on the lower side. So obviously, whenever there is a lower input voltage, see, we know that the power is constant. If we are decreasing the voltage, suppose we are taking the input voltage as on the lower side. So obviously the current will be increasing on the input side. So that is why obviously if current will increase, depending on the overall impedance, obviously there would be a losses, means I square R losses, right? And within this full operating range, because the range is quite big from 110 to 285. So whenever actually we are designing this type of charger, we are taking the full load efficiency at the nominal input voltage, right? Plus minus 10%, means suppose from 200 to 250. So that will give you a best efficiency. But yes, obviously on a lower side, we are not getting that much efficiency. So that is why they have actually written here the efficiency is less than 92%. And you can see there is a one more input, that is a current THD. So all the time is, what is the THD? THD nothing but total harmonic distortion. So this is also a concept that we are actually supposed to, the quality of current actually we are providing. So whatever the spikes, means in the previous slide, actually you can see that here due to power factors, actually there the spike is actually increasing, and there are multiple high frequency components also are there, because obviously our main goal is to means we are switching, right? There is a high frequency switching actually we are applying. So due to this high frequency switching, it actually affect the input current as well. So that is why THD means 3%, that is a total harmonic distortion, right? How much distorted your input sinusoidal waveform is, right? So that is they have given less than 3%. So mostly a good design should have less than 5% THD, right? So they have given 3%. So obviously it is good. And whenever the THD will be in the lower side, and we are getting the higher efficiency. If the input current is distorted, right, due to your whatever you are you're switching your means the secondary side, whatever you are doing, if this is distorted, obviously the overall efficiency will be decreasing. So that is that type of design specifications actually we are following nowadays. In case of means any wattage from 1 kilowatt to 10 kilowatt, right? So we are following this trend, we can say. Now there is a one concept, that is V2G and G2V. So what is this? So basically these type of structures actually we have not implemented in India, that is V2G and G2V, means vehicle to grid and grid to vehicle structure. Suppose there is a, see, all we know that in the morning time, right? In the morning time, the grid usage is very less, right? So on that case, in the morning time, from supposed to be from 10 to up to 5, right? From 10 a.m. or 9 a.m. to up to 5 a.m. So 5 p.m. So that would be the cost of the electricity is little bit less. And after 5 p.m., obviously the electricity cost will be slightly increasing. Means it depends on the area, obviously. So whenever suppose there is a, means the concept in the this type of concepts actually we are applying on European market especially. So suppose your vehicle is charged, right? Suppose your vehicle is already charged, and suppose there is a grid requirement. So on that case, your vehicle battery pack will actually obviously means we can extract the power from the vehicle and gives back to the grid, right? So there is the technology, that is bidirectional power flow actually we are doing. So for this actually we are using a bidirectional converter. So you can see that type of charging stations. So in the charging stations itself, we are using a bidirectional converter. Means there is a bidirectional power flow happens. So obviously there should be a AC to DC converter. Obviously, suppose the vehicle need charge. So on that time, whatever the charger application means, whatever the charger circuits actually we are designing, so that will work. So we are taking power from the grid, and obviously after conversion, it will charge your DC battery pack. Now suppose whenever we need to charge the, not need to charge, actually need to power flow on the grid side. On that case, we will actually use a inverter circuit. So from the battery, DC voltage is extracted, and by using an inverter operation, that is DC to AC conversion, we are actually fed back the supply to the grid. So that is the main concept behind the V2G and G2V. So obviously there are multiple papers are there. I am not talking about the papers. Real design notes actually are there. Means you can easily design this type of bidirectional converter if you follow the steps, right? So I am not going into deeper on the design point, obviously. So that is the main concept of V2G and G2V. And also we are using some communication protocol as well, right? Because see, without communication protocol, we can't feed back the power to the grid. And also there should be a security, right? So any type of charging stations we are plugging, and our every vehicle data, right? Vehicle is connected with the CAN protocol, and each data actually it is circulating. So obviously there should be a safety of data, as well as whenever actually means when the communication will established, on that case only this type of bidirectional converter works. Suppose in case of vehicle charging, as well as power feedback to the grid, right? So for this actually communication should be there. So this type of means whenever there is a grid failures or there is a need of power supply on the grid, so on that case actually this type of system works. But obviously in our India, so there is already a very few percent actually we are using the EV, and the grid demand is very high, obviously. So this type of infrastructure we have not developed yet. Yes, but we are working on this. There are two type of standards actually, you can see that is IEC 61850 and there is a IEC 15118. So these two standards actually we are following on this V2G G2V structure, right? I hope you can get my point. Now we are also researching on the wireless charging part. But see guys, everything obviously means whenever we are doing this type of wireless charging, so our main source is our grid, that is 3-phase or single phase AC source, and our main requirement is our DC, right? Already in the circuit, inside the circuit actually we are using transformers for this type of conversion. You can see that already I told you that from AC to DC there is a conversion, right? AC to DC conversion, then again there is a DC to DC conversion. But whenever actually we supposed to do this type of wireless charging, right? So obviously that would means that would require the inductive charging. Obviously that should be there. Means we have to work on AC, right? So you can see that there is a 2 to 3 conversion happens, right? There is a DC to AC conversion, then AC to DC conversion, right? So there are too many conversions actually we are doing. So on this conversion, obviously there would be a efficiency drop. So already, we have seen that there is if I am talking about the overall efficiency of the system, right, from a AC supply to a battery charging, means actual energy we are getting. So there is a 70% efficiency, means there is a 30% less efficiency. See, normal charger actually we are getting nearly around 90%. So nowadays the charger would give you 90 to 93% charging efficiency. And in case of wireless charging, actually we are getting the 70% efficiency, right? So obviously, in an efficiency point of view, it is not feasible. But yes, we means obviously researchers are working on this, that how actually we can improve the efficiency. So obviously that depends on the receiver, and obviously whatever the trans receiver actually we are using on this case, and the resonating coil actually we are using. So obviously it depends on that design, right? So In the foreign countries, actually, we are doing this type of things. Means prototyping, actually, we are doing. But in case of India, actually, we have not developed any type of prototype also. Right? I am prototype means I am talking about commercial basis, Arki. So that is the two thing actually are on, we can say, on in R&D phase, right? Wireless charging as well as V2G and G2V. And onboard and offboard charging are widely available, right? So there are multiple designs are there. So I am showing you some of the designs. 1 second, guys. Let me share the screen. I hope this one. So I hope, guys, you can see the screen. So this is the application note of means ST Microelectronics. There are multiple companies are there. You can follow those reference design as well. TI also there, Texas Instrument, onsemi. There are multiple designs are there. So I am showing you a 7 kilowatt design that is for EV and HEV onboard charger reference design. So if you follow, suppose you want to enter into this charging industry, so obviously you can follow this type of uh, design notes. So you can see that there is a huge circuit basically, and there are multiple types of conductors actually, components actually we are using. So obviously, whenever actually you will be get into this type of designs, then only you can get the better clarity. So on this design, basically we have used PFC circuit, right? And in PFC also, there are multiple means types of topology actually we are using. So obviously in case of 7 kilowatt, we have to use more efficient one because we have to put the efficiency more than 90%. So I'm just giving you a small overview. So this is basically obviously microcontroller based, and this type of components actually they are suggesting. So everybody have their own portfolio. Microcontroller, MOSFETs, gate driving ICs means whenever actually we are suppose we are using MOSFETs, IGBTs, right? So this type of power switches, right? To control this type of power switches, microcontroller is not means not having that much capability. It is generating the pulses, obviously, whatever the pulse with modulation or the whatever the signals actually we are generating by the microcontroller unit. So this much current is not capable to drive those type of high voltage, high current MOSFETs or IGBT. So that is why actually in between this, we are actually using a gate driver circuit. Basically boost the voltage and current. Means whatever the signaling actually we are getting from the microcontroller, we are boosting those voltage and current capability. Because whenever suppose we need the high frequency switching operations for this type of MOSFETs, so there should be a ample amount of voltage you have to apply. Supposed to be in case of MOSFETs, we are applying 15 volt, 16 volt, right? And also there is some current requirement also to drive those MOSFETs. So that would be done by gate driver circuit. So obviously in every company's portfolio, there is a gate driver circuits and also MOSFETs, IGBTs, PWM ICs, obviously microcontrollers are there. So in this type of application note, actually, you will get the overall block diagram, right? How actually we are, why actually we are using this block, supposed to be PFC, supposed to be DC to DC converters, magnetics design. So this type of design notes actually follows everything. See, in this actually you can get it that AC to DC plus PFC, you can see there is a DC to DC, and again there is a DC to DC conversion. See how the 32-bit microcontroller is controlling all the phases, right? There is a temperature sensing, there is a current sensing. So everything is sensed properly. So there is a AC to DC PFC, you can see, and there is a DC to DC primary, and after that there is a DC to DC secondary. So there is also in DC to DC also we are using a most efficient topologies. There are multiple topologies are there. Forward converter, flyback converters, push-pull converters, and the recent one that actually we are working on LLC converters. So in LLC, basically resonant converters, actually we named it as a resonant converter, LLC resonant converters. So basically why actually we are using this, I am just giving you a small overview. In whenever actually we are doing this type of switching application, high switching application, on that case actually we are losing some energy or some power on the switches, right? Whatever the switches actually we are using, there is some switching losses actually happens. So basically to reduce those type of switching losses, actually we are using this type of resonant converters. So to boost the efficiency, actually we are getting this. So in this DC to DC conversion, in this overall conversion, mostly we can get up to 95 to 96% efficiency, obviously depending on the power, output power. But yes, we can actually get around 96% efficiency. So all the things actually controlled by the microcontroller itself, right? Okay. Now they have actually given what are the basics of the rectifiers. Means from that you can say means get the basic theory of the overall PFC circuit. Why actually we are doing PFCs. In PFCs also, what are the types of PFCs actually we are using, right? Single boost, interleaved, totem pole. So that are the type of PFC circuits actually we are using. Now in case of boost converter, so there is a lot of derivations actually they have given, right? Means from these derivations actually you can get the formula, means how to calculate the inductor values, how to calculate the capacitor values, right? So whatever the values, how to actually get the transformer values. So this type of values, calculations, everything actually they have given on the design notes. And there is a control algorithm also they have presented, right? So this type of design notes actually you can follow. Means obviously you can get a very good in-depth concept on this, right? If you are really interested to design or get into this charging industry, right? You can obviously follow this type of design notes of any companies I am talking about. So you can get a better clarity and obviously an in-depth knowledge. So now actually, okay, we completed with the charging section. So whatever we have yesterday, we have seen that what are the charging profiling, right? How actually we have to charge, trickle charge, pre-charge, CCCV, and obviously there should be a charging termination. And also all the datas, all the things actually can be would be controlled by the CAN protocol, right? So there should be a BMS to charger communication, right? After that, all of these things actually means all these steps I am talking about, so it will be implemented, right? So is there any question up to this charging technology? Don't worry about the attendance, guys. Means after 8:30 actually you will get the sheet, right? From the sheet actually you can give your attendance. Don't worry on the attendance part. So please give your feedback, means if there is any question on the charging infrastructure. Because I know guys in means first year, second year, third year, fourth year, we are not going into that much deeper on the design note especially. So if we are supposed to doing some hardware arrangement, so obviously that will be on a basic level, right? On the final year also we are doing this type of projects, right? Charger designs, inverter designs. I'm talking about for electrical electronics or maybe some IoT related projects for in case of ECEs. So on the embedded part also we can do this type of control infrastructure. Now actually I want to show you, one second, the AIS 156. So let me share. Okay, I can show you from. So I hope you can see, yes, my latest slide. So what is AIS 156? Basically there are multiple automotive standards actually we are using to launch your battery pack, to launch your vehicle, to launch your BMS, or to launch your charger, to launch your traction inverter, to launch your DC-DC converter, which is actually related to the EV ecosystem, right? They have to certify with AIS. You can see that there are multiple AIS standards are there. In case of electric vehicles, there is a AIS 038. Then after that, there is a multiple revision also we have taken. But the ultimate one, that is AIS 156. That is the final one. You can see that AIS 156. And AIS 156 are also there for traction battery also. Means how actually, what are the safety features your battery should have, right? So that type of means technologies actually we are using. There are multiple other type of techniques also are there. Means sorry, certification are also there. Suppose to be you are supposed to launch your BMS, right? So for the BMS there is a AIS 004, that is for EMI EMC. So for EMI EMC, for traction inverters, for BMS, for DC to DC converters, so for this type of electronic circuits, for chargers also, you have to certify this type of EMI EMC testing standards. So there are 2-3 companies are there, not companies, they are PSU type bodies. In northern region there is a ICAT, right? ICAT is the institution which actually certify this type of electric vehicles or traction batteries or other components, which I have told. In Mumbai or Pune, there is MNRE. So on that also, we not MNRE, that is ARAI, sorry, ARAI. So that is also on the automotive standards. They are also certifying the vehicles as well as the batteries, BMS, and other components. So there are two to three this type of entities actually are there, but there should be a certification cost. As of my knowledge, whenever actually we were doing for the certification for traction batteries for one model, right? Suppose the model is 90 volt 100 ampere hour, right? So that is roughly around 9 kilowatt hour model. So that was basically we have done for three wheelers. So not 90 volt, actually 72 volt was there. 72 volt 100 ampere hour, that is roughly around 7.2 kilowatt hour of lithium ion battery pack. So for that battery pack, 7.2 kilowatt hour battery pack, means nearly the charge will be 15 lakhs, right? For one model I am talking about, and only for the battery pack I am talking about. So this type of certification cost actually you have to provide. Means for everything testing, means you have to give 10 to 12 samples, right? So every samples will be tested for different kind of tests. Supposed to be there should be a short circuit test, there would be a over voltage test, there should be a temperature test, drop test, vibration test. Also there would be a IP67 test. So for particular testing they need a particular battery pack. In the vehicle also we are doing this type of testings, right? So for vehicle, obviously I don't know for vehicle certifications, right? But for battery certification, for EMI EMC, for a BMS, right? So we go there for a BMS certification as well. For a roughly 16 series 80 ampere BMS, that was 16 series 80 ampere BMS. So for to doing this type of BMS certification, means I am talking about EMI EMC certification. So it requires nearly 3 to 4 lakhs, right? So it depends on your overall whatever the specifications it is. Obviously, for a big component, suppose like a traction inverters, chargers, suppose 5 kilowatt, 10 kilowatt chargers, also the main certifications amount will be increasing. Now, what are the type of testings actually we are doing? So there are multiple types of categories are there. Oh, sorry. So there is a L category vehicle, there is a M and N category vehicles. So in L category vehicles, actually we are having two wheelers, three wheelers. in M and N category vehicles, we are having four-wheelers, commercials, vehicles. So for L category vehicle, actually we are following EIS 156. For M and N category vehicles, we are using EIS 038. Mostly all the testing are same. Just only 2 to 3 testings actually we are doing extra. But yes, hydrogen emission test actually we are not doing. Thermal propagation test on the on the red marked thermal propagation test we are doing for every, means for L category as well, for M and N, every categories actually we are using this thermal propagation test. Most of the test actually you can see all are same: vibration test, thermal shock test, mechanical drop test, means uh, mechanical drop test for the RESS. RESS means rechargeable energy storage system. That is for, means battery packs, especially they are talking about. For the right hand side, the mechanical shock test actually we are doing in a overall vehicle. Fire resistance test, external short circuit test, overcharge, over discharge protection, over temperature protection, over current protection. So this type of protection test actually we are doing, right? So on this, the main I can say that is IP67 test. So already we know in case of, means a lot of things actually I hope you know about it. In mobile phones also, in some of the gadgets also we are using, everywhere actually we see that is IP67, IP68, and nowadays IP69 also we are supposed to give, right? IP69, IP68. So obviously there should be a meaning, right? How actually we are doing these things. Now for IP rating, that is nothing but the ingress protection test. Now IP67, right? So after IP, there is a two letters, right? Suppose 6561, 6701, 2030, that is. Suppose charger. So in case of charger, there is a IP20 design, there is a IP67 design. In case of, suppose I am using, in case of traction inverter, obviously that is IP67 design. Suppose we are using any kind of inverters, right? Home inverters I'm talking about, where actually we are using fans, force air cooling, right? So that type of cabinets are roughly IP20 rated, right? So what does it mean? You can see that for the first place, right? Whatever the first place, actually it is denoting the solid particles. The second place actually denoting the water particles. So if it is already tested from the water, so obviously it should be dust proof, right? That is why the first one, there is a IP65, 67, 68, right? So obviously if, means we can do 6 as well as 5, right? I'm talking about IP65 rating. Now what happens? There is a standards. In case of solid particles, suppose we are starting with 1. That means whatever the solid particle size, it should not be greater than 50 mm, right? Means, sorry, it would be greater than 50 mm. So that would comes under 1. Now, in 2, basically, this type of designs actually protected from a greater than 12.5 mm, right? Such as finger. So this type of protection actually we are giving as a IP20 rating or IP20 rating. Now there is a 3, obviously. So whenever actually we are increasing the numbers, suppose from 1, 2, 3, 4 and followed up to 6. So we are actually decreasing the particle size, means we are actually compacting the design, right? So up to 6, the last one, right? In the dust particles, in the solid particles, actually there is a last parameter that is 6, right? Above 6, there is nothing. So 6, that it means that it is dust tight, no ingress of dust, right? For 2 to 8 hours, actually they are testing for this. So if the battery pack, right? Not only the battery pack, if it is supposed for DC to DC converters, supposed to be for traction inverters, so that should be dust proof, right? If suppose we are following IP6 something rating. So first one is for solid, second one is for water. So obviously there is a up to 1, from 1 to up to 8, actually there is a water rating actually there. So from started with 1, actually that is protected against the vertically falling drops, right? The second one, that is we are suppose tilting the means object, we can say object, we are tilting the object by a 15 degree, right? So there should not be water inside the object. After that, in case of 3, there is a 60-degree spray, water spray actually suppose we are applying. So there should not be water ingress inside the object. And in case of 4, there is a splashed water from the all the directions. In case of 5, there is a jet spray actually we are applying, means jet water. In case of, so mostly in these cases actually we have seen the IP65 rating is followed. But in case of EVs, I'm talking about in case of EVs, there should be IP67 rated battery packs, traction inverters, onboard chargers, right? So this type of 3 to 4 components should be IP67 rated. Now 6 is for the projected powerful jets actually we are using. Now 7, that is the actually we are immersing the object inside the water up to 1 meter, right? From 15 centimeter to 1 meter, and we have to deploy this object up for 30 minutes, right? Minimum 30 minutes. So after 30 minutes, obviously they will put back from the water, and there should be no water. Obviously they will check the output, if the inverter is working or not, if the battery pack output voltage is working or not, there is any type of short circuit happens or not inside this, there is any kind of fire cases or not. In case of battery pack especially I'm talking about, if there is a short circuit, if there is a fire cases, obviously your battery will be rejected on the IP67 test. The 8 means obviously that would be in 1 meter depth, but the timing is more than 1 hour, right? So that is how actually we are implementing the IP test. So for battery pack, it is very, very important. So obviously you know about the weather, right? So IP68 or minimum IP67 should be required, right, for the battery packs, because we know the hazardous can happen if there is a short circuit inside the battery pack, right? So that is the IP testing. Now there is suppose there would be any kind of thermal runaway happens, right? Any kind of thermal runaway happens inside the battery pack. Okay, before that actually I want to share with you the actual EIS 156 amendment. So that is the EIS 156 amendment 3 as of 2022 revision, right? So that is the L category vehicle. So RESS is nothing but the battery pack I'm talking about. This is fully focused on the battery pack, right? Now RESS means the battery pack with 100% SOC, means state of charge, shall be tested for water ingress protection. Means whenever actually we are doing this IP testing for the battery pack, on that moment the battery should be full charged, and they have written that there shall be no fire or explosion during this IPX7 testing. So why they have given X7? So obviously if there is a water protection is 7, so obviously it would be dust proof, right? So that is the X7s actually we are implementing. So that is the first clause. The second one, that is on battery management system. You can see that in this set means on the standards, the BMS should have the microcontroller based circuit, right? So on the immediate effect, obviously the hardware BMSs we have to reject, right? Whoever is using, that doesn't matter, but if you need a certification, right, so you have to implement the microprocessor based BMS solutions. BMS shall comply EMC standards, that is AIS 004, right? Part 3 means you should have the EMI EMC certification for the BMS. Means For BMS, there should be a separate certification. For sales, there need a separate certifications, right? Any other arrangement, suppose you are using inside the battery pack, for that also you need separate certifications, right? And there is a overall battery certification, right? So obviously, component wise, there should be a certification. Now the third point, that is BMS of this battery pack should have this type of protection. One is overcharge, over discharge, over temperature, over current, and short circuit. So everything will be verified, right? Each of the point will be verified during this testing, right? They will push overcharging, means over voltage charging they will do. They will check that your BMS is operating or not. Whenever actually you are submitting your battery pack, right? So you have to give the all the specifications. So the over voltage cutoff, under voltage cutoff, over current cutoff, over temperature charging, over temperature discharging, every type of protection parameters we have to provide earlier, right? During the submission of the battery pack. So according to your profiling, whatever the profile actually you have given, so on that profiling actually they will test. So obviously there would be a 5 different tests actually they conduct. Now there is a onboard charger or offboard charger certification, right? Suppose we are using an onboard charger, as well as suppose there is be a portable charger. So the charger shall have the voltage cutoff to overcharging. That is the last charging algorithm, or we can say the charge termination point, right? So on the algorithm we have seen that the trickle, then pre-charge, then CC, then CV, then charging termination. So after getting the communication, obviously after getting the BMS data, the charger should stop the charging. Now the second part, the charger shall have the soft start function. So what does it mean? What is soft start function? Soft start means suppose my charger is a 20 ampere charger, or suppose it is a 50 ampere charger. So whenever suppose we are connecting the charger, after communication establishment, the charger is start for charging. Suppose the battery SOC on in range. Suppose the battery SOC is 30%, 40%. So that would be on CC mode, right? Constant current mode. So on this constant current mode, obviously the charging current should be the maximum. That is 50 ampere. So whenever you are starts your charging, on that immediate effect, actually it will not mean it should not goes the 50 ampere at a time. It should gradually increase its charging current, right? Supposed to be 1 ampere, 2 ampere, 5 ampere, 7 ampere, 9 ampere, 10 ampere, right? So gradually increment should be there. So that is the soft start. Now how actually we can control those current in a hardware arrangement? Inside the power electronics, how actually we are controlling this? We are actually controlling the duty cycle of the switching. Whatever the switching application we are doing, whatever the conversion actually we are doing inside the charging operation, right? There is a DC-DC converters, I told you. There is a transformers are there. We are doing step up or step down depending on the battery voltage, right? So we are actually controlling the duty cycle, means the overall on time of the switch, right? I am not going into very deeper on this, but yes, for your information, the soft start is nothing but gradually current increment. So that should be there. Now the third point, that is the charger shall have the pre-charge function to detect the deep discharge condition of the battery pack. So obviously we have seen this type of pre-charge function, right, on the charger design part. Now the charger shall have the input supply variation up to plus minus 10%. So already manufacturer designed this type of battery pack on, means from 110 volt to 285 volt. So this is a huge range. So obviously it comes under plus minus 10%, right? Means whenever actually you are a designer, you are a hardware designer or you are a product designer, on that case, obviously you have to keep in mind of this type of clauses, right? The fifth point, that is the charger shall have the earth leakage detection. Now, what is earth leakage detection? So obviously we are giving a line, a neutral, and an earthing point, right? So if suppose actually there is a every charging in the whole charging industry, I'm talking about if we are using a portable charger. So there is already a connector type arrangement actually we are having. So that type of cables actually we are using, which are having this type of earth leakage detection with protection systems. Means there is a on off switch. Suppose there is a leakage current is flowing from line to earth, right? Or maybe neutral to earth. If it detects any kind of leakage current, so it will actually switch off the charging. Means from the input side itself. I'm not talking about on the output side. Means on the whenever actually in the input actually we are pushing the power on the input, suppose AC to DC rectification. Before that actually we are using this type of earth leakage detection circuit, right? So this type of detection circuit actually follows the IS 12640 part 1. The last one, that is the onboard charger. This type of charger shall have the communication with battery. Means obviously that is a BMS. So your BMS should be the means software BMS. Obviously there is a communication, means CAN communication. And also there is a charger. In the charger inside also we are using CAN communication, right? So there is a separate hardware actually we are using for that. Now let's come to the second, that is a clause 6.11, that is a thermal propagation test. Actually, in the battery packs, actually, we are increasing the gist actually I'm giving you. The main purpose of this thermal propagation test is, suppose there is a external heating elements we are applying. It may be on the summer, suppose you are just any kind of thermal runway happens inside the battery pack, right? So that type of thermal runway actually they are implementing externally, right? So in this thermal propagation test, actually we are means during the certifications actually we are using a heater. So basically we are using a heater to heat up the cells, especially for one cells arrangement actually we are doing. Suppose in an overall battery pack, we are only applying a heater or a heating to a single cell. And we are trying to do means whatever the thermal runway means, obviously there is a measurement of thermal runway, means the obviously the measurements also they have given. So I'm just showing the method. See, you can see that what are the clause also. The test shall be conducted at the temperature, the ambient temperature should be 25 plus minus 2 degree. And you can see that the SOC means the state of charge should be 95%. That means that is almost full charge. And at the beginning of the test, all test devices shall be operational. Means we have to put a temperature sensors also. Okay, let's see that how actually the arrangement would be. See, this is basically the arrangement. For pouch cell or the prismatic cells, actually we can use the film heater. Already I have shown you how the film heater looks like. So we have to apply, suppose there is a pouch cell or a prismatic cell. So in one side actually we have to connect the heater, right, on the cell surface, and the another side actually we have to put a temperature sensor, right? So basically measure the cell temperature. If there is a cylindrical cells, so there is an arrangement also they have given. If suppose you are using a slim film heater, so in one surface actually we are putting this heater, right? On another surface actually we are applying this temperature sensors. Suppose in the cylindrical cells actually there is another type of heaters actually we can use. Suppose winded type heaters also we can use. So the temperature sensors actually put it on the cell vent especially. So that is how actually we have to design the battery pack for thermal runway test, or we can say the thermal propagation test. So for the thermal propagation test, we have to design a battery pack separately. Obviously, overall structure should be same. The cell, all the designs would be same. Just you have to put a heater inside this. By using these heaters, actually, we will initiate the thermal runway section for one cell. And how actually we are determining that thermal runway happens. Now, so that is the detection of thermal runaway. How actually we are detecting? So they have given 3 point, right? If the measured voltage, so obviously on that time we will measure the cell voltage also. If there is a sudden drop on the voltage, suppose there is a 4.2 volt, right? In the full charge, if I am taking a NMC cell, it is nearly around 4.2 volt. If there is a sudden drop in the voltage, right, that is 1 point. The second point is the measured temperature exceeds, right, the maximum operating temperature defined by the manufacturer. That means we have to put a temperature value, the measured temperature. Obviously, as we know that above 80 degree, 90 degree, actually, the thermal runway started. So obviously we will give nearly around 100 degree or 120 degree temperature. So that is the second point. Third point, that is dt by dt, means rate of change of temperature with respect to time. That should be greater than equal to 1 degree centigrade per second. Means the temperature rise on the thermistor, whatever the temperature sensor actually we are applying on the cell surface, means that means the cell temperature, the inside cell temperature should be, means increasing at a rate of 1 degree centigrade per second. So now you can see that how thermal runaway can be judged. The first one, that is both 1 and 3 are detected, or both 2 and 3 are detected, means the third point should be matched, right? The 1 degree centigrade per second increment should be there, and either 1 or 2, right? So if these two things, or we can say these two standards actually we can follow, so obviously they can actually detect, that is thermal runaway. And how actually we are judging this thermal runaway, right, or the thermal propagation test, means what is the passing criteria. So there should not be any kind of fire cases happens. So that is the main thing, right? There should not be any fire cases happens. You can see that there is some procedures also they have given. The heating procedure, that is nothing but the after installation of the heater, the heater temperature should be up to 300 degree, means that would be more than 300 degree. If and also suppose we are applying this 300 degree temperature up to 30 minutes, right? So obviously we will take this as a initiation method, right? Means obviously we can take this as a thermal runway also. Suppose the temperature is 300 degree and the time already 30 minutes gone. So on that case, we will stop the initiation method. So that will be the main clause of the thermal propagation test. And it is a very important test, right? Mostly on this case, the NMC one actually gone away, because most of the NMC cells actually will give you a thermal runway as well as the fire cases. So mostly that is why actually we are using LFP. Mostly actually we are using LFP, or we are using a cylindrical NMC cells, right? On that cylindrical NMC cells, actually we have seen that there is a short circuit happens obviously, but there is no fire cases happens. Very few companies sales actually, which actually means this kind of manufacturers actually use a different kind of electrolyte properties, right? On that case actually we can meet this criteria. Okay, now there is some another things actually we have to follow. So these points are also important. The traction battery pack design and manufacture guidelines, right? Means obviously this type of battery manufacturer should have the proper manufacturing date, year, right, month and year you have to provide. So there should be a traceability document should be there. You have to submit those traceability document, whatever the 12 to 15 battery packs actually you are providing, you have to give those traceability documents. Means that I will show you what thing actually they need. Obviously whatever the cells actually we are using inside those battery pack, that should be certified by a NABL means obviously affiliated lab, right? And the certification standards, that is IS 16893. So this type of standard should be there. This type of certification should be there for the cells. Now the cells actually should have a minimum 1 cycle of charge and discharge at C/3 current rate. Means you have to provide this data, right? 1 cycle data of C/3 current rating, right? For cells I am talking about, suppose we are using 1000 cells, you have to give 1000 cells data. Suppose we are using 1000 cells for one battery pack, you should have all the traceability. So in this battery pack, there is a battery pack part number, right? Manufacturing ID, that is the thing. Inside this battery pack, we are using this 1000 number of cells. That 1000 number of cells should have this data, right? So that is how actually you have to present those things. So means that in this certification also, there is a lot of things, right? For means preparing samples for certifications is very tough, right? But yes, after certification, many companies actually, I have seen that they actually decrease their quality. So I have seen also this type of manufacturer also. Okay. So in the certification itself, means in the clauses itself, they have written that the battery shall have a pressure release vent, obviously, to avoid the building up of internal pressure. Whenever suppose there is a short circuit happens, in case of NMC, in case of LFP, it may be any circumstances. Maybe thermal runaway happens due to short circuit, over voltage, over temperature, and any could be the reason. So on that case, actually, there is a internal gas, obviously there is internal gas buildup happens. So from the thermal runaway session, basically we have seen that how actually the cell encapsulation happens and the gas are ejected from the cells, right? So whenever actually we are designing a battery pack, we are designing a IP67 battery pack. So this is basically a airtight, dust proof, waterproof. Obviously, if there is no pressure release vent, what happens? If a thermal runaway happens, so your battery pack pressure will actually build up and it is rapidly increasing, right? If there is nothing on this or this type of pressure release vent, actually it can burst, right? So that is actually, I want to show you which type of pressure release vent actually we are using. So this is basically the pressure release valve or vent actually we are using in the battery pack. So in case of four-wheeler battery packs, actually you can see that is the top cover or the outer cabinet. Actually we are using this type of pressure release vent. We can use 2 to 3, obviously depending on your overall application purpose. Means how much pressure actually your battery can create on the thermal runway. So depending on that pressure, actually you have to use the number of pressure vents. So whenever that pressure means obviously it is IP68. Most of the pressure release vent actually IP67 or 68 rated, right? Means there is no water particles can move through this pressure release vent. Now there is a plastic encapsulation actually we are having. There is a metallic also we are having. So most of the time actually we use metallic one, right? So we actually not use plastic one. So this is a pressure release vent actually we are using, and there is other clauses are also there. Now the battery pack should have minimum 4 temperature sensors. Minimum, that is the minimum one. And suppose in these temperature sensors, it suppose detect 60-degree temperature. Suppose it detects 60-degree temperature, then there should be a audio visual alarm system, right? Which actually give you some alert, right? This is for the user safety. Actually, we are using. So obviously BMS shall gradually cut off the battery pack from the, suppose there is some supply. If suppose we are charging, on that case, if suppose there is a loading actually we are doing, or maybe in the there is a standstill condition, the audio visual alarm should be there in case of increment with the temperature if increases above 60-degree. Now on that case, in the market actually there is a solutions actually are there. That is a audio visual alarm system. Means it has a LED indication with the buzzer. So the left one, that is not IP67. That is basically a IP nearly around IP20 rated. Right. So that is that type of things actually we are not using on EV. But on the right one, you can see that that is basically a IP68 rated audio visual alarm system. Means it needs a DC voltage. Right. From the BMS, actually we can control this audio visual alarm. So actually in the BMS side, actually we have to implement a 12-volt supply. Whatever the battery voltage we are getting, we have to use some small DC to DC converter, right? By using these DC to DC converters, actually from the MCU itself, we can control this signal. So if we are sensing some 60-degree, right, on the NTC, then we will trigger this means audio visual alarm. So that is actually connected with the BMS. And this type of audiovisual alarm just only having a DC input, positive and negative. There is a multiple voltage rating are available in the market, 3.3 volt, 5 volt, 9 volt, 12 volt, 24 volt, right? Depending on your BMS power output, because every BMS means there is a design changes, right? Some of the manufacturer gives 12 volt output, some of the manufacturer gives 9 volt output, someone gives 18 or 24 volt output. So depending on that BMS manufacturer, obviously you have to choose your voltage rating of this type of audiovisual alarm system. So that is also a clause. Now the sixth one, this is actually an active paralleling circuit. This is especially on the active paralleling circuit. Means already we have taken this session, right? Basically wire bonding technique. So on the battery pack design sessions, I have shown you that Ola and Ether is especially using cylindrical cells. See, most of the two-wheelers actually using cylindrical cells. If suppose we are using some parallel number of cells, on that case, we should have this type of active paralleling circuit. So this wire bonding or fusing technology, whatever the parallel number of cells we are connecting with the series bus bars, actually we are using some fusing technology. So that is how actually we can implement an active paralleling circuit. If suppose any one of the cell there is a circulating current due to any reason, it may happen. So if there is a circulating current or short circuit current, then this type of cells will be cut off from the overall battery pack. So for the safety purposes, actually we are using this type of active paralleling circuit. Now also they have written that you can use a fuse wires, you can use a bond wires. So obviously fuse means obviously suppose there is a cylindrical cells we are using, 1,000 number of cells we are using. So that does means it is ready to impossible that to use fuse, right? So there is another technique that is fusible nickel strip actually we are using, or fusible bus bars we are using. And another one obviously wire bonding technique. Now the seventh one, that is a cell to cell spacing. In case of cylindrical, there is a different spacing. In case of pouch cell, in case of prismatic cells, the spacing, the whatever the space actually we are applying, that should be different. In case of cylindrical cells, that is more the gap between cell to cell should be more than 1 mm. Right? There should be a gap. If suppose we are applying active thermal management system, we are supposed to be using serpentine tube. So obviously we have to means we have to take minimum 1.5 mm gap between each cells. But in case of prismatic cells, it is roughly around 1.5 to 2 mm gap at least you have to provide. So most of the time inside this gap actually we are using a thermal pad, 2 mm thermal pad, 2.5 mm thermal pad actually we are placing. See, this type of gap actually this type of gap can be done via cell holder. Whenever we are designing the cell holders, so we are designing cell holder in such a way that we can prevent this obviously gapping. So that is the seventh point. Means this type of things your battery pack should have. Then only they will certify. Keep the certification. Otherwise, we will not get. They will reject your battery pack. Now the 8th point, that is the battery pack should have an additional safety fuse. Means rather than you are using a MOSFET mechanism, anything you can use, but rather than the use in BMS itself, you have to use a separate fuse or battery disconnect system. Now actually I want to show this to you. I hope you can see my screen. Okay. So this is basically a safety fuse for two-wheeler, three-wheelers. Actually, we are using that upper type of models. So there is a blade fuse on the right-hand side top corner. That is the 40 ampere blade fuse actually we are using. And on 150, whatever the written 150, that is nothing but a bolt down fuse. So bolt down fuse, actually for higher current rating, we use this type of 150 ampere fuses. For lower current rating, we are using this type of 40 ampere blade fuses, right? So fuse holder also we are having with this. Now the lower one, that is for four-wheelers. Four-wheeler battery packs, actually we are using this type of BDU. BDU is nothing but battery disconnect unit. So this type of BDU also we are using. So actually it is controlled via BMS, right? There is a contactors or fuse actually we are using. So there is a means contactor based also there, means we are using a contactor, right? That would be controlled via relay. And also there is a mechanical fuse are there, this orange one in this BDU, overall BDU, the orange one is a fuse, right? So I think in the YouTube also you can see this type of big fuse actually they have implemented at the end of the EV manufacturing process, right? At the last actually they put this fuse on the BDU unit. So this type of we can say, rather means obviously there is a primary protection, right? PMS, but we should have this type of secondary protections from overcurrent or short circuit. Basically we are using fuses for overcurrent protections, right? So this type of secondary protection should be there. Okay, now we left with some 2 to 3 points. Now, the 8th point we covered, there should be a circuit breaker or safety fuse additionally. Now, the 9th point, that is the battery manufacturer shall have the traceability document. Means we have to submit the documents, means all the test, all the cell testing datas, all the battery pack testing datas, BMS datas, overcharge, over discharge, everything, the cutoffs, the charger stop start data. So everything would be there. The 10th one, that is a adequate protection of cells in case of regenerative braking. So whenever actually we are doing regenerative braking, so that is nothing but a charging process, right? So regenerative braking, actually this current is not fixed. Whenever we are charging the battery pack with a charger, the current is fixed, that is up to CC level. But whenever we are doing regenerative braking, depending on the motor specifications, we are getting the charging current, means regain energy. So regain energy, obviously that is nothing but a regain current, right? So regain current, obviously there should be a regenerative braking. See, if we have a charging current protection, we will obviously select the motor current, or we will select the charging current depending on these two parameters, right? So that would be there. If there is a charging protection, obviously there should be a regenerative braking current protection. Now the 11th one, that is also a critical one, the data of these critical parameters of the battery pack. So what are the critical parameters? The cell voltage, the charging discharging current, the temperature. So these 3 to 4 data should be means locked inside the BMS, or it can be on the remote server, right? So that is why actually we are using some IoT system to basically get the data from the BMS, right? From obviously from the CAN communications actually we are using. So we are getting all the data from the BMS, and we are actually pushing this data to the server. And you should have at least 1 month of data. It may be on the BMS or it may be on the server. at least 1 month of data, right? So that is the overall AIS 156 for, especially I have shown you the battery packs because it is pretty much important than the inverters and the DC-DC converters, because for inverter converters actually there is only AIS 0004, that is EMI EMMC standards. That is a very small test actually they are doing. But for battery packs there is a huge number of tests actually we are conducting. So depending on these test results, actually they will certify. Otherwise, they will reject your battery pack, and there is only one chance actually you will get for the certification. Means suppose your battery pack reject for one time, second time will only get a chance, right? After that, you have to resubmit your samples. You have to resubmit the payment as well, right? So there is a clause, obviously. So before going into the certifications, you have to carefully design all the things, as well as you have to carefully test all of these things in your lab itself, right? Before going to the certification. So I hope you guys can understand from the AIS 156. If there any question, please ask now, right? Okay, you can take a roughly 5 minutes break on this, right? And also please ask question on that if you are having any doubt. Okay, guys, I think there is no question on the AIS 156. So I will be starting the new battery technology trends. Let me share the screen again, 1 second. Okay. So yes, I hope you can see my screen, obviously. So first, that is the solid state battery. So now this type of solid state battery means I'm talking about for EV. For EV, actually, the solid state battery is means gaining the popularity nowadays. So every manufacturer, I'm talking about cell manufacturer, are working on this. See, there is a multiple battery pack manufacturing company. More than 1,000 number of players are there. Many startups are there in the battery pack design. But there is a very few cell manufacturing companies are there. And I think in India there is nothing actually. Uh, I think 2 to 3 companies are actually working on this. Ola, also there is a Log9. So 2 3 companies are there. They actually have started earlier also. So very few companies are there who are actually doing R&D on the cell manufacturing division, but there is a huge scope on cell R&D as well. But yes, that is for especially chemical engineers, right? So obviously for engineering guys, means I am talking about for electrical, mechanical, CS guys, obviously that is not in our scope. But yes, you should know about the technology, how actually we are changing those technology, how we are improving the battery technology, right? Now in the solid state battery, this is also a lithium ion battery, but the only difference that is the solid electrolyte actually we are using. So what is the detailed mechanism? So the left one is a normal lithium ion batteries actually we are using, whatever means normal NMC, LFP, NCA, these type of chemistries actually we are using. And in case of solid state also we are using the same chemistries. There is nothing different. Only different it in the separator, or we can say the electrolyte. Now in case of lithium ion, normal lithium ion batteries or traditional lithium ion batteries, we are using a separator. Obviously separately we are using 2 components, right? One is separator and another one is a, what is this? That is electrolyte. So gel type electrolyte actually we are using, means that is a liquid type, liquid gel type. And there is a porous separator actually we are using. In case of solid state batteries, actually we are replacing those separator with a solid electrolyte. So this solid electrolyte actually works as a separator itself. So obviously we are replacing 2 component with 1 component only. And as a result, whenever actually we are using this type of solid electrolyte, actually we are getting an advantage. So this is the conventional battery. You can see the cathode and anode actually deep into the electrolyte. But in case of solid state, there is a solid electrolyte actually we are using inside this anode and cathode. So whenever actually we are using this type of solid electrolyte, we are actually reducing the risk of the leakage. Whenever there is a short circuit happens, there is a mechanical stress actually we are applying on the cells. It may be due to vibration, it may be due to any kind of mechanical impact actually which are applying inside the battery pack, due to which your means your cell may means obviously puncture, right? Many this type of punctures, means this type of faulty cells actually we have seen it on the market itself. So if your design suppose doesn't have any kind of mechanical stability, on that case actually this type of cell puncturing actually we observes from the market. So that is also an advantage whenever we are supposed to use a solid electrolyte. And in this type of electrolyte, obviously suppose there is a very hard mechanical impact actually we are doing, but there is no fire cases. In case of NMC chemistry also, there is a zero chance of fire. Obviously there should be a thermal runaway, obviously there should be a temperature rise up inside the cells, but there should not be any kind of fire cases. So obviously this is a extreme hazards actually we have seen on the lithium ion batteries, the fire. In case of NMC, especially in case of LFP also, somehow in LFP what happens, suppose your battery pack temperature is increases and there is a pressure buildup, obviously the heat buildup, obviously, and there is some kind of plastic parts actually we are using inside the EVs. So somehow actually it takes or it catch the heat and it will actually turns into a fire. So in case of lithium NMC, there is a very risk of using this type of cells, NMC, conventional I am talking about. But yes, we can easily replace those with solid state batteries. And we can easily actually test those thermal runways and other things actually we can pass on that type of testings. Now basically there is the same chemistry. Nothing is actually means different from that. only thing is the electrolyte, the solid electrolyte structure. So that is the LiPon we are using. So there's a multiple types of means research actually going on the selection of the electrolyte, solid electrolyte. So obviously during discharge, the ion moves back from the cathode, right? And from the charging, that is cathode to anode, there is a lithium ion flow. So that is same as the means conventional one actually we have seen. Now, what are the type of solid electrolytes actually we are using? There are three types of electrolytes already we are using. That is a sulfide based, oxide based, and the polymer based. So there is a pros and cons of every type of electrolytes. So obviously, if suppose someone is a very high ionic conductivity, what does it mean? High ionic conductivity. So we have seen the C rate, right? See, what is the C rate? That is a charging discharging rate. If we replace the sulfide based electrolyte, right, or if we place this sulfide based electrolyte, we can even charge our battery pack up to 3C 5C rating. Means your battery pack roughly take 10 minutes of time to be full charged, guys, and you are not actually damaging your cells if we use this type of sulfide based electrolytes. That is, this type of cells having high ionic conductivity, means lithium ion can move very fast. That means higher charging current, higher discharging current. So we can get the life better, as well as we can actually do the fast charging or fast discharging, but it is chemically unstable with moisture. If you are unable to do IP68 or IP67, on that immediate case, actually it produces the toxic gases, that is the H2S. So obviously, means the reactivity with lithium metals also need the engineering. Means the lithium trapping is also done on this type of sulfide based electrolytes, right? So there is a pros as well as there is a disadvantage also. In case of oxide base, there is a chemically very much stable, but it has a lower ionic conductivity, but yes, more than the conventional one. Whatever the conventional one we have seen, that is maximum 0.5 C. In suppose there is a 10 Ah cell, the 5 ampere will be a charging current, should be the maximum charging current, but it should be more than 0.5 C. So it is started with 1 C charging, means your battery pack should charge with 1 hour. Within 1 hour, actually, we can charge the battery pack easily. Now the third one, that is the polymer based electrolytes. Now in this type of electrolyte, polymer based electrolyte, actually it is very easy to process, flexible, low temperature. And what is the main disadvantage of this type of we can say polymer based electrolyte? It actually means require heating, means whenever actually the temperature, means ambient temperature is on the suppose upper side, suppose 50 degree 60 degree, then only it will give you good performance, right? Means suppose I am deploying a EV on the summer. In the summer it will actually give you a good performance, but in the winter actually it will not give you. So for means demographic point of view, actually this type of polymer based will not be the good option, will not be the good option. But yes, we are actually researching on a different kind of solid state electrolytes also. See, we already have fixed the anode side and the cathode side, that is graphite based anode, and that is a suppose NMC, LFP or NCA based cathode. Just we have to do research on the electrolyte property. Now actually there is a okay, so material already I already gave the same example. On the anode side we use graphite, silicon or lithium metal, or on the electrolyte we have taken that sulfide oxide polymer. On the cathode we use LFP, NMC, NCA, LCO. So this type of chemistries actually we are using. Now, what are the advantage of this type of batteries and what are the disadvantage? So advantage obviously having the more impact, higher energy density. In the NMC cell, actually we are getting the energy density around maximum up to 250 watt hour per kilogram. So by using this type of solid state batteries, we can get up to 30%, 25 to 30% more energy density on the NMC itself. Suppose we are using LFP. So actually we can reduce the weight up to 25 to 30%. So already you can observe that we can reduce the weight as well as the overall area. So we can get up to 25 to 30% more range on the same, suppose we are using same area or on the same weight. The improved safety, that is non-flammable. So obviously there is a less likely to leak and reducing the fire risk. So that is the main risk actually associated with the NMC one. So that is why actually we are choosing LFP, low energy density. But yes, so by improving this electrolyte property, actually, we can use now NMC cells as well in case of EVs. Longer lifespan. As you know, we are having roughly maximum 800 to 1000 cycles in the NMC. Roughly means that is also degrading the cells as well, means 90% degraded. Sorry, 10% degraded, right? But in case of LFP, obviously there is a more number of cycles actually we are getting. Nowadays, some LFP cells actually giving 5000 cycles, means huge. 10 means more than 10 years actually you can get a life. 10 years, more than 10 years. If all the other external parameters are likely to be followed. So in NMC also we are getting a 2 times more lifespan. Suppose we are using NMC solid state batteries. So on that case, we can actually improve 2 times more life. So on that NMC actually, we are roughly giving 2 to 3 years of warranty. Right? In two-wheeler, three-wheelers, we are using NMC and we are giving 2 to 3 years of warranty. So we can give them 5 years of warranty. So obviously our main purpose is to get the battery life, obviously, and a good range. So in EV, our main purpose is this thing because the battery pack is much costlier. So that is the main cost of EV, the battery packs. The fourth one, that is the wider operating temperature. So that is also an important one. Most of the cells, whatever the data sheet we have seen up to now, most of the cells give the charging temperature limit up to 50 degree or 55 degree maximum. Discharging limit, temperature limit I'm talking about, up to 60 degree maximum. But using this type of solid state, actually we can go up to 70, 75 degree. So 10 degree, 15 degree delta, that is huge. And obviously you know that means it is ionic mobility will be there, right? So that is dependent on the fast charging. So high C rating charge, high C rating discharge. So our main focus is high C rating charge because we are actually means we are limited, right? There is a limitations on the charging, on the fast charging especially. So by using these solid state batteries, actually we can overcome this disadvantage. But what are the disadvantage of this? That is the manufacturing challenge and costing. These two are actually means this is actually internally related. Why this is manufacturing challenge? Because we don't have that type of production lines. So we have to start with the production line. So somehow 15 years, 20 years back, when actually we have started with lithium ion battery manufacturing, on that time also, just I am giving you a rough idea, guys. Whenever actually I have started my career on 2021, on that time, on 21, the battery, that means this LFP cells, as of my knowledge, the LFP cells 100 ampere hour, 3.2 volt prismatic cells, 100 ampere hour, actually that time the price was nearly around 4,000 rupees. And nowadays, means at present scenario, this is roughly 1000 to 1200 rupees. Means that is drastically decreasing. 3 to 4 times decreases just after 4 to 5 years. Right? Just after 4 years, you can see that it is nearly around 1000, 1200, 1300 rupees. So that is the means production, right? That is the manufacturing feasibility. So obviously we have to start, at least we have to start. So after 2 years, 3 years of the manufacturing, whenever actually we will improve the process. So obviously we can actually meet the lithium ion normal conventional models. And the interface problems, actually, whenever actually we are manufacturing the cells, on that time, actually this is a solid. The anode is also a solid, the cathode is also a solid, aluminium copper. So there is an aluminum copper plate or foiling we are using. Inside this, we are using the solid electrolyte. So whenever actually we are suppose pressing those things, whatever the manufacturing process actually we are using, so if there is no good contact between these connections, so obviously your charge cycle or discharge means overall cycle life will be decreasing. So there is a challenge, that is the same challenge, that is the manufacturing challenge, right? There should be a good contact. So obviously we can overcome these disadvantages very easily. Means I know. Now there is a case study. Mercedes actually are researching on their AMG high performance powertrains, especially EQ based vehicles. EQ based means the high class vehicles. So means high safety, obviously high performance vehicles. They are actually applying this kind of in solid state batteries, which can give actually on the same area, same weight, it can give more 25% driving range. And they are actually expecting to get 1,000 kilometer of range. So that would be a remarkable step. Means a EV with a single charge, it will give you 1,000 kilometer of range. Right? 1,000 kilometer, I think 1,000 kilometer is more than enough in a single charge if it can give 1,000 kilometer. So that is the remarkable step. Actually means they have not launched actually, but they are expecting. Now the solid state battery progress, there is the companies who are working on this. QuantumScape, that is also a big company. They are working on the lithium metal plus ceramic separator. So they are actually changing the separator, or we can say the electrolyte property. So this QuantumScape actually the partnered with Volkswagen, and they are mainly targeting on the EVs and high energy density. So I think Volkswagen will basically will be means after 2 years, nearly 2027-28, you can see the Volkswagen sales actually you can see on the EVs. Now there is solid power. They also use sulfide based scalable production, means they are in actually production phase. They already have completed their R&D phase. So they basically partner with BMW and Ford, and they are actually doing testing on the 100 ampere hour cells. Toyota also using oxide based solution, and they are prototyping cars already. They have shown they are targeting to launch this type of solid state operated card on 2027 to 28. Samsung is also working on this, that is a hybrid polymer and oxide based electrolyte. They are targeting the cell phones. So already we have seen a new technology, that is silicon one. Basically we are getting 7,000 mAh cells, but that is also not a safer on. But yes, Samsung also working on this solid state batteries, so they will be targeting the cell phone market. Now there is two more companies you can see. So basically these companies are basically focused on the IoT system, and Prologium actually focused on the Mercedes-Benz. So they are also working on the semi-solid format, not a full solid format. They are working on the semi-solid format. So this is the roughly working actually we are doing on this. One second, there is some question. Yes, the attendance link actually will be shared. Don't worry on that. Already shared. So you have disconnected. Don't worry on that. You will be getting the attendance link, guys. Okay, this the research is going on in the solid state. Now there is a sodium ion battery. So we are actually switching from the lithium ion, to the sodium ion. So now this is a twist, right? On the lithium already we have told that on the lithium extraction there is a lot of carbon footprint. There is a lot of safety factors. There is a lot of, we can say, energy wastage whenever we are testing these things. So carbon footprint, energy wastage, safety. So all of these things actually are means why actually we are move on to the lithium ion. So upcoming 5 years, within upcoming 5 years, actually we will be seeing this sodium ion battery, and very soon. What is the disadvantage? I will show you what is the main disadvantage of this sodium ion. So if we can improve, obviously this will be the next level solution you can get. Same phenomena we are using. So anode cathode working are same. Basically here our sodium ions move from anode to cathode and vice versa during charging and discharging, and we will use a electrolyte, suppose sodium based electrolyte. So that will basically allow the sodium ions for this movement, right? Separator, obviously we have to use the same management, everything will be same, just the electrolyte will be changed, and the obviously the cathode property will be changed, right? So I am not taking into deep that during charging how electrolyte how sodium ion moves from cathode to anode, right? So these things are same. Especially I will be showing you yes, the material which we are using on the anode, that is a hard carbon, that is basically graphite based, again carbon. uh, and again there are 2 to 3 materials actually you can see. The cathode materials also you can see layered oxides, right? So Na3V2PO43, this type of chemical compounds actually we are using. The electrolyte, that is a sodium NaPF6 in carbonate solvent actually we are using, and in the separator, that is the not porous one, that is uh, this type of film type separators actually we are using for the short circuits. So these are the rough chemical structures now actually we are researching on, right? But mainly what is the disadvantage and advantage with respect to lithium? So the energy density actually we are getting a pretty much lower, but that is not lower than the LFP chemistry. You can see that I am taking a NMC chemistry reference on the higher side, that is 200 to 250 watt hour per kg. But you have seen guys, from the LFP chemistry, we are getting the same exactly the sodium ion. That means sodium ion can easily replace the LFP chemistry on from the lithium ion. uh, Means from the lithium ion the LFP can be easily replaced, and the cost is very lower. Means lithium is on higher side, 3 to 4 times less costly actually the sodium ion is. Mean we can get a very low cost battery solutions. The material abundance, that is very high. Means sodium is widely available, not like the lithium and cobalt. So see, only the material that is a lithium and cobalt, because of this material that is not widely available, that is why actually the lithium ion battery cost is pretty much higher. The safety is very means far better than lithium ion. There is no means there is no option of fire cases, and also we can get means we can get a very good cycle life. This is on the improving state. If we can replace the LFP, obviously we have to think on the LFP battery pack life as well, 5,000 cycles. So obviously we have to take on that part also. So that is also under means R&D actually. The commercial status is obviously lithium, and we know in the mainstream, and that is emerging, means on the R&D phase. Now, what are the key players they are actually working? So CATL China, Mercedes actually using the CATL cells, not means not the SIB. They are lithium ion actually they are using. They have launched their first commercial SIB on 2021, but actually they have not commercialized yet on the EVs, especially. Means I am talking about only in EV. No one actually have selected these cells because of obviously the cycle life and the energy density. So that is why actually EV manufacturer have not selected yet. But yes, they are means this Faradian UK based company, that they are actually developing on the high energy storage, means higher energy dense SIBs, and that is basically acquired by Reliance Industries Limited. So they are working on these SIBs. So we will see near future that Reliance also have launched their sodium ion based battery pack or cells. And there is multiple other companies are also there. ISC Bangalore also working on the solid state sodium ion batteries for better stability. So means already we have seen the solid state lithium ion. If we can get the solid state SIB, then we can get a better life cycle. As on lithium ion also we have seen there is a better life cycle. So whatever the life cycle we are getting now, if we replace those one with solid state SIB, then we can get a better life. And also we can get a better energy density. So ISC is working on that. Now there is another one, that is aluminum air battery. So that is basically a non-rechargeable battery pack. Means as a theoretical concept, it can give you a 20 times more range. Suppose one EV is giving you a 800 km of range. 20 times more it can give. Means in one, suppose you are just installing one time battery, you can get nearly around 16 to 18,000 km of range. Right? Means obviously the single battery actually without any charge actually you can means take it up to 1 year, 2 year. And aluminium also a very we can say abundance material, right? It is widely available in the market. So that is the anode and cathode actually we are using. In the anode, basically we are using the aluminum plates where oxidation basically occurs. And in the cathode side, we only take up the oxygen to the air. So that is why it is named as aluminum air battery. And the electrolyte solution, that is we are using aqueous solutions. We are using NaOH or KOH for the aluminum ion transportation. And also we are using the separator, the same thing actually we are using. So the main purpose is the aluminum movement. You can see that is a OH minus movement you can see on the overall reaction. But the main advantage, that is the energy density, guys. Theoretically we are getting 8,000 watt-hour per kg. And I means don't know how much we can meet, but if we can meet at least 2 to 3,000 watt-hour per kg, then also we can get. Also in the swappable, whatever the swappable solutions actually we are having, we can play on the swapping part, because aluminum easily can be recycled. So there is a recycling process we can develop on this matter. Also we can see already aluminum is widely available, so the costing will be pretty much reduced. Whatever the charging cost actually we are using for lithium ion battery packs, if on that charging cost, right, obviously that would be slightly higher, but yes, if we can actually means design a cost effective aluminum air battery, then obviously we can actually replace the battery even after supposed to be 10,000 km. That is not an issue. So that is the eco-friendly material, non-toxic materials actually we are using, and it is easily recyclable. That is very low cost. It is very much cheaper than lithium and cobalt, and it is a safe chemistry. That is also the main point. In case of sodium ion also, in case of solid state battery also, in case of aluminum air also, the main thing, the main safety is a non-flammable solution, because fire is the main risk. What are the disadvantages? That is non-rechargeable, right? The most designs are in the primary stage, so that is non-rechargeable aluminum air batteries actually we are using. Now there is a one thing, very low power density, the last one. Low power density means we cannot see, obviously this is not non-rechargeable, but whenever we are actually discharging, the discharging rate also will be very much less. Less means maximum actually we can get as a lead acid battery pack, means 0.1 C, 0.15 C, right? So obviously we have to design a higher watt hour battery pack. high watt hour or high kilowatt hour or high ampere hour battery pack we have to design to meet the initial demand, whatever the current actually we need. Whenever actually we are accelerating the EV, to meet those demand we have to increase our capacity, means ampere hour rating, so that we can actually meet those criteria, the current criteria. So that is the big disadvantage of this type of aluminum air. And also there is a CO2 contamination also there. So CO2 from air actually reacts with the electrolyte and forming the carbonates. So day by day actually the performance is reducing. Suppose we are expecting a 8,000 watt hour per kg, suppose we are getting, and we are expecting a nearly supposed to be 10,000 kilometer. So it may reduce up to 5,000 as well. So means we can say that is a unstable solution. So that is also the research is going on this, that how actually we can do a stable one. So that is the main disadvantage of this. And anode corrosion also one of the main disadvantage, because aluminum actually reacts with water, whatever the water vapors or moisture actually we are having. So these actually cause a self discharge. Means suppose we are not charging or discharge, obviously there is no charging. Suppose we are not discharging, that is on standstill condition. On that case actually the self discharge rate is quite higher than the lithium ion, the other chemistries. We can say it is nearly actually acting like a NiMH battery pack. So NiMH basically roughly having 30% self discharge rate. So that would be also the same 25 to 30% self discharge rate. So we have to improve these things, right? Non rechargeable, obviously it would not be rechargeable. Means as of now I think maybe in the near future we can do a better things on the aluminum air, or in the sodium ion also we can replace the, means if we are using a sodium ion, so obviously we can easily replace the lithium ion. It is means on a cost basis, on a safety basis, right? So that is the thing, that is the type of batteries and everything actually we are battery technology actually we are doing research on this. So guys, if you have any question, please ask. Okay, there is a question. Can a battery pack of a vehicle could get damaged while off-roading after getting a hard impact on it? Okay, that's basically depend on your mechanical structure. Whenever suppose we are doing off-roading, obviously there is a lot of vibration happens. So whenever actually we are doing the IP67 design on the battery pack, so on that case, there would be a vibration test also there, mechanical shock test also there. So if this type of battery pack would pass those vibration test, drop test, mechanical shock test, right? So obviously it cannot be damaged. But yes, obviously depend on the means how much mechanical means stability your battery pack is, and also how much the impact is. But yes, normal off-roading actually doesn't hamper the battery pack, means that would actually can't damage your battery pack. Okay, one question more, that is why Indian automotive is focusing on the BEV as they are not completely developed yet. And why don't they focus on the HEVs? They are better alternative at the current state of time. Yes, you are right. HEVs are better. But guys, for HEVs design are more complex. There is a IC engine, there is a motor, right? There is a overall gear ratios, there is a PSD. So whenever actually we are using this, there is a complex manufacturing setups we required, right? So whenever the components is on the higher side, that is a design rule in any cases. It can be any kind of product, it can be vehicle, it can be a AC, fridge, any kind of product suppose we are designing. On that case, if your component count is more, so there is a risk failure, right? So basically, whenever actually you will be getting into the industry, then you will get, there is a DFM actually we are doing, design mode failure analysis. Also, there is a manufacturing or process mode failure analysis. So whenever the component will be more, there would be a chance of process mode failures. So that is why actually we are pushing BEVs, because BEVs are easy to design as compared to HEVs. That is the main concept. Means that is why actually we are pushing BEVs. And also, guys, we have to reduce the carbon footprint. HEVs are not actually, they also emit the carbon, right? CO2s. So that is also we are more focusing on the BEVs. But yes, BEVs nowadays, I can say this is almost developed. If I am talking about the four-wheeler industry, yes, if they used a better quality cells, irrespective of the there is a cost versus quality means fight always we are doing in, especially for Indian market. I don't know, in Indian market only we are implementing these things, cost versus quality. But in case of foreign market, actually the quality would matter, right? So quality is on the upper side against cost. Which type of battery is useful? Means I can't get your point. Means which type of battery is used or useful? Any other question, guys, on this? Which type of battery is used? In which, in for which applications? You are talking about EVs. So already lithium-ion batteries actually we are using. Means I hope you have not attended the previous sessions. The lithium ion only we are using, guys. This is the new battery trend actually I am talking about today. So that would be a new battery trend. But yes, we are obviously stick on the lithium ion itself up to now. Vida battery means, can you please some elaboration on this Vida battery? Any other question, guys? Can you please explain on the okay, Vida scooty use battery is good or not safe? Oh, they are also using lithium ion, I guess. Means you're talking about, okay, let me search. Just give me 1 minute. Okay, you are talking about the flexible one. That is the flexible battery subscription plan. Means that is the same thing, the swappable technology. That is nothing but that the 5 years warranty actually they are giving, or a 60%, 60,000 kilometer. And they are already giving a degradation over 30%, performance degradation over 30% or 5 years or 60,000 kilometer. Means this is the warranties actually they are giving. They are also in the lithium ion chemistry, same chemistry actually they are giving. So obviously means the Hero is also using same, Ola Ether also doing same chemistries. So obviously means it depends on your battery structure, how actually we are designing those batteries, which type of cells actually we are using. But yes, they are giving a good warranty. That means 5 year warranty. Obviously, they are using a LFP chemistry. That is a safer chemistry. Because in case of NMC, most of the companies is giving 2 years or 3 years of warranty. So they are giving 5 years of warranty. Obviously, that means they are actually using LFP. So LFP have a, obviously there is a no risk of fire on the LFP, and also uh, it will give you a more life cycle. Okay, is there any question? Anything related to charging? Because we are actually about to end. So tomorrow will be our last session on the EV part. So on the EV part, actually we will be on the last session. Basically, we will be covering the drive system, traction inverter system, DC-DC converter system. So that will be also focused on the electronics, basically power electronics based, means how actually we are controlling the voltage, controlling the current, means the overall system. Also, we are how actually we are controlling the speed of the motor. So we will see on the last session, that will be on tomorrow. So okay, there is no further question. So I can conclude the session, guys. Thank you so much. Thank you so much for joining. Okay, Shushmita, I am ending up now. And good night, guys. Have a nice day.
Yeah, thank you, sir. Thank you so much. We'll meet again by tomorrow at 7 p.m. Good night.
Yeah. Thank you. Thank you so much.
Yeah, so the students, we are running up for the day. Meet again by tomorrow. Thank you.